Hello, have you seen the new MLX Python library that was released by the machine learning group at Apple? Apparently, it's very good for speeding up machine learning computing using your Apple Silicon GPU. But aside from machine learning workflows, it supports a subset of the Numpy API. In this video, I'll be exploring if we can actually speed up scientific computing workflows using the MLX library. This is Vincent Codes Finance, a channel dedicated to coding for finance research. If that's something that interests you, please subscribe. Okay, so what is this MLX library? According to their website, it's a NumPy-like array framework designed for efficient and flexible machine learning on Apple Silicon. And it's designed by the Apple Machine Learning Group. So the main use case is obviously for machine learning workflows. But that's not what I'm looking at today. I want to see whether I can use it for my own scientific computing workflows. What really caught my eye when I saw their website is that they state that the API closely follows NumPy, with only a few exceptions. One thing that's important to note is that it has lazy computation, which is actually very good. It's a feature that other libraries have implemented. For example, Polars, the data frame library, also does lazy execution. The idea behind lazy execution is that your code is not executed right away. It's only executed once you need the result, once you ask for the result. And until you request those results, the library only keeps track of all these tasks that you want to be performed on your data. And then when you ask for the result, it figures out the most efficient way to get to that result. One thing that they have that's pretty good is that the operation that you define on MLX, they can run on any of the supported devices. So in this case, that's basically the CPU and the GPU on Apple Silicon. And why is that important and why is that different from other frameworks like, for example, JAX? Well, it's because of the architecture that we have in Apple Silicon, because arrays in MLX, they live in shared memory. On Apple Silicon, GPU and CPU, they share the same RAM. They can use the same memory. So that means that there's no data transfer when you do an operation on the CPU and then a following operation on the GPU. In order to install MLX, you can use your package manager of choice. So either pip install MLX, or if you're using Poetry add MLX, or if you're on Conda, you can install it by making sure that you use the proper forge. So Conda forge. And it might have been obvious from the start and from the introduction, but MLX really requires an Apple Silicon computer, so M1, M2, or M3. In my case, I'm using a M3 Max with 64 gigs of RAM, so this is what we'll have in terms of benchmark for our tests today. So what I'll do today is I'll take a workflow that I have in NumPy that I've also optimized using Numba. So if you're not aware of Numba, Numba is another library that makes Python code fast, especially NumPy code. And what it does is that it compiles just in time. So it has a just-in-time compiler. It compiles your functions and make them run faster on the CPU. NumPy also supports GPU, but only with NVIDIA GPUs, which you don't have on a Mac laptop. So in this case, we'll have two comparable. For our workflow, we'll have a NumPy-based workflow, a Numba-based workflow, but that runs on the CPU, and a MLX workflow. For my example today, what I'll use is I'll use a simple simulation-based workflow where I'll be simulating time series processes. So I'll be simulating an AR3 GARCH 1.1 process multiple times. And then for each draw, I'll be computing the t-statistic for the null hypothesis that the average return during that sample is 0. So just a basic t-statistic. If you want to see the code that I've used, it is on GitHub. Just look at the video description, where you'll also find a link to written instruction for this tutorial. Okay, so let's first look quickly at our NumPy code. So what we'll be doing is simulating an AR3 GARCH 1.1 process. If you're not too familiar with those processes, that's fine. Just think that it is a numerical workflow where we are simulating things. So we will here be first simulating shocks drawn from a random normal distribution. Then using these shocks, we'll be generating GARCH shocks, so shocks for which the volatility has some persistence. And then these GARCH shocks, we'll use them and feed them to an AR tree process, which is an autoregressive process. So it has some autocorrelation between shocks. These tree functions, they're put together in this simulate AR tree GARCH11 function, where we are simulating the random shocks, passing them to the GARCH shock function, which returns GARCH shocks from these shocks, which are then fed to the AR function, and that will give us our simulated values. We are using a burn-in value of 100. So the first 100 observations of each sample will be discarded. And then we'll compute the t-stat based on the white heteroscedasticity robust standard errors using the standard formula. So this is what we have in terms of function. Now let's look at MLX. What is involved in converting it to an MLX code? Well, in order to use MLX, we have to import it. So we'll import mlx.core as mx. And then after that, it is pretty much just replace all the np by mx. So if we compare our code, so down here I've got the MLX code, up here I've got the NumPy code. So for simulate shock, exactly the same thing, except that now here I've got mx. And for some reason, this random normal function in mx doesn't take the size argument, but the shape. It's a shape parameter that you have to pass. So this is what I've done in order to make it work. You'll also note, you can also see with my typing and the type-ins that here I'm actually returning an mx.array, not an numpy array. But otherwise, everything is the same. If we come here to our GARCH shocks, it is exactly the same code, except that here I'm using mx.zeros. I'm taking an mx array as input and I'm returning an mx array. But other than that, nothing has changed except for this one here, the square root function. It's now an mx square root function. If we go at the AR function, the autoregressive function, again, it is exactly the same thing, except that we are using mx arrays, we're using mx.zeros, and that's it. This function is exactly the same as well, except for the return type that is an mx array. And finally, for the t-statistics, well, it's almost the same, except that the std function doesn't exist in MLX, so I had to implement it myself. Fairly easy to do, but that was some extra work. And that's it. Now, if we compare to the work I had to do to make it work with Numba, let's look at the Numba code. So for Numba, you have to import the decorator njit, so to make sure that that each function is compiled just in time, and then the p-range operator to allow for parallel loops whenever appropriate. Right. So if we look at our simulate shock function, all I had to do was to add this njit decorator, and that was it. For the GARCH shock, again, not much work to do. All I had to do was to add the decorator. There's nothing that can be parallelized in this specific GARCH shock function directly because it is based on the time. So you need to use the previous observation in your results. So you have to do it sequentially in any case. So for the autoregressive process, that's the same thing. All I did was to add the njit decorator. There's nothing that can be parallelized directly here, except for all these vector operation that will be run in parallel for the different samples. But within one sample, everything is sequential, so there's no parallel there. This function is also exactly the same. And then where it got a bit more complicated with Numba is that to compute the t-stats, well, I needed to have the mean on this axis here, which is not possible in Numba. You can only do it on the other axis. So I actually had to implement my own means and my own standard deviation d-mean, so starting from a d-mean array, in order to compute that t-stat. So once I had that t-stat done, then this is how I got to computing my t-stats. This was a bit extra work. So this is where I use the p-range function, because these loops here and in this standard deviation calculation, these two loops can be done in parallel. So on every element in parallel, there's no dependency there. So that's the code that we have. Now what I'll do is I'll import all of these functions and I'll run some benchmarks on them. So I'll try different sample size. So I'll start with 250 or 500 observations in terms of length for my series that I'm simulating. And then I'll be simulating 1,000 to 1 million random draws for each of these functions. So here are the kind of default parameters that I'm using, and I'll be passing that. Before I execute anything and start timing for my benchmark, I will call these Numba functions so that they get compiled. So we won't have the compilation time, at least in theory, shouldn't be in our benchmark. And then it's just a basic loop. So we've got 2 embedded for loops over the different n's and t's that we'll use for our parameters. And then what I'll do is we'll just start the timer, call my functions, happen the results so that I'll store them. I'll show you a graph afterwards. I'll make sure that I delete them just in case that I run out of memory, although I shouldn't with these models. And then I'll display the time. I'll do that for the NumPy first, then Numba, and then MLX. One thing that is important with MLX is I will then convert it to a NumPy array. I will take that into account for my time. There's a conversion here that will happen, and then I will have the data in the same format. So it's kind of a penalty here, but it's also to make sure that the code gets executed until I request the result. If you remember, nothing actually happens with MLX. So I have to request the output for it to compute the result. So it should be fairly comparable. One big limitation or one big difference to note, however, is that in NumPy and Numba, when you generate random numbers, everything is in float 64, so 64 bits. That's not something that you can change. At least I haven't figured out how to change it. If you know, let me know in the comments. But keep in mind that the precision for the NumPy and Numba, it's 64-bit, whereas for MLX, the largest precision float that is available is float 32. So this is what we'll be using. So keep that in mind. If you've got a scientific workflow that requires 64-bit floats, then MLX won't be for you, right? There is some limitation here. That is the highest precision float that is supported by MLX. So this is what we're using, 32 bits for MLX. Okay, so now let's run the code. I have a small notebook here that will display our stats. Keep in mind, both scale for the Y and X axis are in log scale because we've used really different scales in terms of number of units. So the first here is for the sample draws where we had 250 observations per sample draw. What we see is that once you get really small, well, there is some overhead involved with MLX and Numba. So for really small sample size in terms of the number of simulation draws that you're making, then there's not much advantage here. And as you progress, we see that, yes, there is a benefit to MLX. It is the fastest. It's even faster than Numba. Keep in mind this is one workflow. Your result might vary depending on the actual CPU that you have and the actual computation that you're doing. This, as far as I know, is not what MLX is optimized for. It's optimized for matrix calculation and other kind of machine learning related workflows. But as we can see here, it can actually speed up some of our NumPy-based workflows, such as this one. If we look at the longer time series, so 500 observation. Again, MLX is not a big winner when you've got really small simulations, so things that don't take too much time. But as you kind of max out the GPU and you use it to close to its full potential, although I have no way of checking. If you know how to check how I've maxed out my GPU on Mac, it doesn't show in System Monitor, so I have no idea how busy it is when it's running. So let me know in the comments if you know. But in this case, what I see is that when I push it to the limit, then I get some benefits, but the benefits are somewhat marginal. Again, I have an M3 Max, but I don't have the one with the most GPU cores, so it's not maxed on that dimension. So maybe with an even more powerful GPU, it would be slightly better. But like, to me, whether I'm gonna use MLX over Numba, not clear what's preferable here. One thing that I did notice though, when I'm running the MLX pipeline or the MLX workflow, is that my CPU usage is really low. So I haven't tried it, but it's possible that you could be running both MLX and NumPy workflows at the same time on the same CPU. Not sure whether you get some throttling issues because of the power usage or things like that. That's something that I'll definitely be testing in the future, but it does seem like MLX could be useful for some use cases. If you've been using MLX for other use cases, please let me know in the comments. I'd be really curious to see what you've been up to with this new library. That's it for today. If you enjoyed this video, please like and also consider subscribing to the channel so that you get notified of my future videos.